Hello, everybody. Welcome back. Many of you, I recognize quite a few names. I'm going to spend a few seconds here getting my screen organized because I just have so much information to share. But while I'm doing that, one thing that I want to recap is last week, if anybody's new, I just want to cover this. Last week, we covered using the Anaconda software as the distribution. Anaconda, which contains Python, and Jupyter. We used the Jupyter notebooks as the interface through which we then opened up a code file, basically, that I created. And then using that code file, we walked our way through some of the sample workshop code. Today's going to follow the same model. The difference is going to be that instead of focusing on just like how to open data, how to view data, how to do some subsets and stuff like that, we're going to switch gears to a little bit more like actual analysis type tasks, where we start looking at like linear regression models and like how do those get formed using Python tools. That'll be the first half of today, and then the second half we'll start doing some basic data visualization. We'll use a module called Seaborn. So I opened my start window in Windows, or if you're using a Mac, it's Finder, and I think it's going to be a little bit different. But last week, we used Anaconda Navigator, right? Anaconda Navigator is the like traditional program. It opens in a window, you click on buttons and stuff. That's one way to open Jupyter, because Jupyter is the interface we want to work with. But today I want to show you a shortcut, and the shortcut also, I think, might help some people who had troubles last week with a few technical things that are a little bit difficult to resolve. I'm going to show you another way to open Jupyter. So if I click on Anaconda prompt, this is it's a program, it's a shortcut, it's a thing that appears in my start when I search for Anaconda, and it should open this black box, this command prompt. Now, those of you that are tech savvy and you're familiar with command prompts, it's worth noting this is not the default command prompt for your computer. Mac users, I'm sorry, I have no idea what this looks like on a Mac. You'll just have to wing it. But just be aware, this is a slightly different command prompt. And here's what we can do with this. So I'm in my base user directory. I can just start typing Jupyter space lab, Jupyter lab. Now, unfortunately, I cannot make that any larger on my screen. I'll type it in the chat real quick. But this is my command. So in the Anaconda prompt that I opened, let me do it again. I'll type the Windows key, Anaconda prompt, which opens the command prompt for Anaconda specifically. And the first thing I'll type is Jupyter Lab. And when I do that, I'm going to hit enter. It opens my web browser, it opens Jupyter, it launches the Python kernel, and it does all of those steps just real fast. Now I'm going to make my browser a little bit smaller. If you ever have issues with if you're on a computer that uses Internet Explorer, or you want to switch browsers, like you want to use like Firefox, for instance, how do you do that? Here's one thing I want to point out. In the Anaconda prompt window, because if you try to like go to Firefox, open Jupyter Lab using the URL, you're going to run into a few issues of like, what's the token? So in the command prompt, that information, at least on my screen, is right here. And you can, at least on my computer, I can copy paste that, and I could copy paste it into a like another browser, into Firefox. I don't know if other browsers work, Safari or Opera or anything. I just use Chrome and Firefox. But that's just a little diagnostic tool for you. If you need to switch browsers, you can copy paste that and move it somewhere else. Hopefully you don't need to do that today. Oh yeah, if you're being prompted for just the token, then you can copy paste this. You could also just copy paste the whole thing into a browser URL bar, and it should resolve if the browser's designed. Now that's getting way into the weeds, and there might be a lot of technical issues depending on individual people's situations. I just wanted to point this out as like, this is a place to look for stuff. I'm going to go back to my browser and make my browser full screen. And now you might see a screen like this, depending on what you did last week, or you might need to navigate around using the windows or the folder icons that are up here in the top left. And if I click on the folder, the tiny little folder option, this will take me to my user directory. And what you should do, if those of you that have all the workshop files downloaded and hopefully in one place, you should navigate to the location where you have those downloaded. So in my case, it's in the downloads folder because I didn't move them. I just downloaded them and left them there. So I'm going to click on my downloads folder, open it up, and then I see all the files that we have for today. Intro to Python was last week. This week will be Python for statistical modeling and plotting data. I can double click on that, and then it opens on screen. Eventually. It might take a few seconds to load, but it should get there. Let's start. Make sure that the code runs. And by that, I mean, so in my case, I'm going to hit Shift Enter, and you should see this blue icon. This is just a lightning fast refresher on how this works. This is the cell that's currently active. And when I hit Shift Enter, it will run the code and then advance to the next cell. And now we're going to get to part 0. This is where we need to make sure that things really work for us. So part 0, I'm going to import a bunch of packages. Don't worry about what they all do necessarily. We're going to use stats models for statistical modeling. We're going to use Seaborn for data visualization. And last week we used pandas for opening data and manipulating data. And pandas is going to be the first one we use. So when I hit Shift Enter on this cell, it may take a second to run because it's importing a bunch of packages all at once or a bunch of modules. But once I get that to run successfully, and assuming there were no errors, if there were errors, then you might need to restart, you might need to reinstall Anaconda, or you might need to install the packages from scratch if you're in a strange environment. I can talk about all of that stuff way later on, though. But for those of you that were successful, the next thing, recapping from last week, using the data frame object that we're going to create. We're going to create an object from scratch and assign it the value PD read CSV. This was at the top of the first workshop. This was where we imported the data set. So this is literally using the pandas module, the function read CSV to read the data. And then we had an option for index column 0. That way we didn't have a superfluous column with row labels. So Shift Enter twice, Shift Enter to use df.head, and then we inspect the data. And then we can see like, okay, cool, it's successfully loaded and the data is stored in the data frame object. And then we can see the variables. And if you forgot, the data is a youth risk survey of like who from these youths, these teens, have they been in a car with a driver who was impaired by alcohol? And then some other factors that we can look at to see what are the factors, what are the variables that might be predictors or indicators that someone is likely to engage in that risky behavior. That's kind of what we're going to build towards from a modeling point of view. That's also what the data was originally collected for. Scrolling down a little bit more, we have this big block of code. Don't worry about the details. We included this last week as well. But what I'm doing, just run this cell if you were successful before. Shift Enter, and all I've done, and this will be for instructional purposes, I have recoded things like female 1 is now like the text female instead of the number. That's all I did was I created some duplicate columns where I have text data instead of numeric indicators. That can be useful because sometimes that's what your data will look like. So I wanted to have both sets of options available to us. And I used slightly different variable names for each of those different variables. Do these commands also recode the other direction? They can. So what I would encourage you to do is like the way you would decode that information. That's a good question, Jill. Is what's happening here is I've got some variable da 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 da. This replace function. So then you can go to like pandas replace, and what I would do is like, okay, let's read through. The function is very robust. It does a lot of different things, but you can say like what you want to replace, what you want to do, and like generally the answer is yes. You could convert a number to text, text to a number, something to a Boolean. You could replace some values with null. You could like evacuate values from the cells. You could do a lot. That's kind of why I said like in the annotations, don't worry about it, because like that gets into a lot more detail. But the way you would do that from a like a professional point of view is like, okay, I see a function doing a thing, let me go to the documentation and see like how else I can tweak it to do what I want. That's like the broad way I would approach that. Great question. Okay, in the chat, because I think you're all the types of nerds that I like. Tell me, what is your favorite or preferred statistical model? I will say mine is a Poisson regression. What types of models do people use in your work or for fun, in your analysis? But I want to get a sense of like the depth of analytic models you all work with. Linear mixed models, ooh, yeah. And it's okay to say like I don't. Like that is absolutely fine. All right, cool. By the way, we're going to keep things simple today. We're going to do a little bit of ordinary least squares regression, and then we'll do logistic regression, which I think is a pretty common thing for social sciencey people to use. I'm not going to go into the really deep stuff of like the more advanced models, but I do want to talk you through that in Python land, a very common approach for like specifying the model is the same regardless of what type of model it is. The details are different, so you have to pay attention to the details, but the broad structure is the same. And let me switch back to my slides because I have a couple slides that visualize this a little bit. So just watching on screen, in Python, you can think of this as having 3 steps. So like a linear regression model, for instance. To create that in Python using the module stats models, we end up having effectively 3 steps. We specify the model, we fit the model, then we inspect the model. And each of those are 3 distinct components for stats models for almost everything. Scikit-Learn, like really fancy pants Google machine learning libraries like TensorFlow or Keras, those types of things. They all like once you like get the details sorted out, it's still these 3-step components. Specify the model, fit the model, then inspect it. And to clarify like what that means, like if I'm doing a linear regression, specifying the model literally just means defining what your formula might look like, or telling it which variables are going to go where and what your dependence, your independence, yada yada yada. Fitting the model is where you actually find your coefficients, your estimates, your parameters. Now, I mean, in this case, this is the OLS, the matrix transformations, basically, that find the coefficients. But whatever it is, this is all part of part 2, fitting the model. And then inspecting is where we look at like residuals. We actually look at the coefficients, look at the F statistics, see what the p-values are and stuff like that. And we start to get into residual analysis. So what we're going to see, and the reason these slides are set up this way is so that you can see how these functions play out. We're going to talk through these functions. But to do the specify, fit, inspect, there's one set of functions, then you build upwards, then you build further. So this example here, and we're going to spend most of our time today on this type of code using the stats models module or package, if we want to call it that. That's what we're going to do most of today. But just be aware, let me scroll to the next slide. Let's say that you're using Scikit-Learn, which is another extremely popular machine learning library in the Python environment. It's not as great at like hardcore statistics. It doesn't conveniently give you the same stuff, but it does a lot of other things pretty well. Like it follows the same procedure of specify, fit, inspect with its different functional setups. And that includes, like, if you've heard of neural networks in the context of machine learning and deep learning and stuff like that, a neural network is fit the exact same way. You specify your model. There's only a few options we have to do. We'll put one in the code. Then you fit it. Then you can score it or inspect it. So just remember, like a bunch of you mentioned a ton of different types of models and quite an array of pretty cool stuff. They're going to follow the similar procedures once we dive into that, or once like you start building up towards that. Today, I want to keep it simple to we'll start with ordinary least squares regression, simple linear regressions. And then we'll go to logistic regression as like the most advanced thing that we actually talk about. And then it's up to you to build upwards later. So let me switch back to my code. So part one, R, style, formulas, linear modeling. Lots of notes. What I want to point out is that there are two distinct packages in the stats models website. Okay. Just watch me on screen. Stats models, API reference. So here's the website. There's two different ways to do stuff. So let's say that you magically knew all this in advance. Like, okay, I need to do a regression. Here's my OLS function. This is one way to do ordinary least squares regression. This is using the stats model, the base formula, which in our code, we called that SM. I skimmed past it real fast, but it's SM. That's what we used as the abbreviation. If I close these annotations and I scroll further down the API reference, now I've arrived at a model package, which we're going to call SMF. So stats models formula. They have a lot of overlap. They're largely the same. They do a lot of the same stuff. They're used in different cases, but we're gonna use both of them. But I want you to understand that these are two different ways that you can approach modeling. And in this case, there's a lowercase OLS. Capitalization really does matter. And this is the one we're going to start with because last week I asked, what tools have people used? And a lot of you had mentioned stats, SPSS. R was a one that got mentioned quite a bit. The formulas package might be the easiest starting point for some people because it allows you to write out your formulas in a way that's probably familiar to you. And then we'll switch to the other one after that. So I'm just letting you know there's these two distinct components of the stats models module. So switching back to my code, let's start putting it together. SMF. SMF is our stats models formulas, and then the OLS function. So I'm going to continue. Stats models formulas, OLS. Inside of our function, we have two components, formula, data. Formula is a string, so I put it in quotes. And then all I need is my dependent variable, squiggly line, independent variable. That is the general syntax for writing the formulas. I provide links in of like various components of like the stats models webpage has links to how to like formulate these models in a complex way. We'll get into that, but just know there's supplemental resources that help you build out. So SMF, stats models formulas, OLS, our formula is age dependent variable with an independent variable of smoker. And then we just define data equals df. Let's run this. Shift, enter. And like that, this meaningless block of information to us as humans is our model. We have specified the model. So now the model exists as a formula. Now, to be honest, it doesn't really exist anywhere. So the next line of code does matter. I'm going to create a model object and assign it that value. That way we can start working with the model. So shift, enter. Okay, cool. I created the model object. The next thing, and this is going to be a whole bunch of steps. We're going to put it together in a succinct way in just a few more lines. But now, remember, the first step was specifying the model. Second step is fitting the model. So I simply take model dot. So I have a method from the model function. I could just type this, type fit. Ooh, I could do a regularized fit if I wanted to. I'm not going to for today. So fit, open close parentheses. Now, what is it fitting to? Now, it's some modules, like you could put in a new data set here if you wanted to. So if you have specified a model, but you have new data, you can fit the model to the new data if you want. So in this case, it is fitting the model just to the data that we've already told it about in our specification step. So shift enter. And now, finally at long last, we can do results.summary. Shift enter. Now we've gone through that process of specify the model, fit the model, inspect the model. This is our inspection results. Like, okay, give me the summary of the results. And OLS regression tells us our model type, tells the method of fitting. We see some p-values, some r-squared, really low r-squared, I think, coefficients. And so now we see an ugly version of what is a regression model output. Let me scroll down a little bit further. So print results summary. So I put results summary inside of a print statement. The reason I do that is it does some tidy formatting for us. So shift, enter, and now I see a much cleaner organization of the same info, which if you're an R user, if you use R and RStudio a lot for regression models, this is probably a familiar output, a familiar format of getting a regression model all at once. Now, I'm going to scroll down a little bit further. I'm going to put all of that together. And this is how I'm going to do most of the rest of today's code. So all three lines together in a single cell, this is what we'll do, and this is how we'll start to modify. Model equals stats models formulas module. OLS, ordinary least squares regression, lowercase, my formula, my data. Then the results are the consequence of model.fit. And then I have the last command, print the results summary. All of that together, shift, enter, produces my regression table. Okay, I'm going to keep moving. Scrolling on down, let's start making this a bit more complicated. So here, we've got our dependent variable age, which is continuous-ish. I think there's only 3 unique values in the data set. So we have age, we have our intercept. Like, we never specified an intercept. We never said include an intercept. The function did it by default. By default, it's one of those things that's included that we would have to remove. And then we have smoker. Smoker was a, if we look at our data, smoker was the column that's labeled as yes, no. So it wasn't numeric. So now it's telling us the reference group is no, and the treatment, so the coefficient we see is for smoker equivalent to yes. Let's scroll down and let's start messing around with that formula. Scroll down, df.columns, shift enter. This is just one way to get like a quick printout of what are the columns available to me again? Like, what can I do? But building from there, let's make a bigger formula. So model, let me scroll down to smidge so it's more on screen. Model, stats models formula, OLS. Age is our dependent variable. There's a variety of things you can do to start building the formulas. Now, if you've built formulas in R, this will be basically the exact same. But if I don't want an intercept, I can explicitly put 0. If I want to chain together multiple independent variables, I can put a plus sign. If I want to capture the interaction terms between any 2 variables, I could do variable A, colon, variable B, And that basically gives me the multiplicative interaction between them. Or I could use the asterisk, and this is where people sometimes get tripped up. So if I do ride asterisk gender, this is going to give me ride as an independent variable, and gender as an independent variable, and ride multiplied by gender as an independent variable. But you'll notice inside the parentheses, I have 3 variables that are all chained together. Let's just see what this produces. Shift, enter. And now as I scroll down, just like that, with just a small tweak of this formula, I didn't have to change the data. I didn't do anything else special. I've now removed the intercept. I've added in tons of different interactions. I don't know that this is a good model. This is a bit complex. And like, I don't even know if it's like got a good p-value. I'd need to look to see. I guess technically it has a p-value, but whatever. Analytically, you know what you need to do. So this is how we can go from a tiny model with just one dependent variable, one independent variable, simple linear regression, and very rapidly expand to a multiple linear regression with a lot of fixed effects and a lot of fixed interaction effects as well. As always, in my workshops, I try to provide practice opportunities. We're not going to do these practice during these workshops because time is limited, but df.columns is just as a utility there to remind you what the code is or what the columns are. You can replace this with df.head if you wanted to preview the data. That way you could remember, wait a minute, which gender is the one that's text, female is the one that's numeric. All right, cool. And then plug and play, mess around, see how you can edit the independent variables, see if you can generate new models. So from that API reference, that page that I was looking at where I was showing you there's 2 different sections, there's a logit model. So there's a GLM, a generalized linear model function. And in that, we could specify and define a generalized linear model that has a certain family, that is the binomial distribution, that is measured in logits for the purposes of specifying the model. Or we could just use the pre-built logit function, SMF logit. Now I'm using a binary dependent variable, ride, alcohol, driver. This is the risky behavior that we're trying to see. Do these youths engage in this? Let's use independent variables grade and age. Shift, enter. And just like that, this follows the same steps. Specify, fit, inspect. Scrolling down, and now we've got that output just right away. And we can see like it gives us information like, okay, the model is a logit model. The method of specification was maximum likelihood estimation. And once you start getting into more advanced models, that you might really care what that is and might want to change it. There's ways to specify those options. But this is where we can start to see our model information, our log likelihoods, pseudo R-squareds, as well as coefficients as measured in logits. Some people in some fields, when they do logistic regression, they report their coefficients as odds ratios. That's not by default here. By default here, we're getting logits or log likelihoods. So let's go down a little bit further. And what I want to show you is like, you can access components of this. You're not stuck accessing just the table. I'm going to scroll down. I give examples of like, do you want the log likelihood? Type in results.llf. Do you want pseudo R-squared? There's an attribute for that. AIC, there's an attribute for that. Let me use on my screen. So results, period. I'm going to hit tab because that works for me. And I can see like, I want all of these different things. I could get like the degrees of freedom for the model versus the residuals, the F-test. I could get all of these different components and attributes. In this case, I want the params. So params, and it's an attribute. It's not a method. It's not a function. So I just hit shift, enter. And now I have the parameters. And I have the parameters on their own. Now, if you're somebody who likes odds ratios, this is a chance for you to convert this. Let me scroll down a little bit further. I won't implement this in the code, or in like the model structure necessarily. But what I've got here, there was a module. We imported this at the beginning, but I'll type it out here. Import NumPy as NP. NumPy is a math-heavy module. So the NumPy module as NP, which has a function to exponentiate, and it can exponentiate an array of data. So I've got an array. I've got results params. Shift, enter. And now I have the odds ratios representation of those coefficients. So just like if that's something that's valuable to you, I don't ever use odds ratios in my own work, but I know lots of other people do, especially public health people, or at least in my experience so far at GSU, public health people love odds ratios. Python lets you take like, okay, we've got a model, we're going to inspect it now. I see that there are log likelihood coefficients. Let me take those parameters and let me convert them separately using other tools and utilities. Going to scroll down a little bit further. df.head, shift enter. Like, all right, cool. Let's look at this data. Let me try something. With the logistic regression model, which requires a binary dependent variable, I'm going to use so originally we used ride alcohol driver, but now I'm going to switch to using ride, which is yeses and nos. So it's still binary in a conceptual sense, so I'm going to use ride as the dependent variable in my model. And I'm going to close my annotations, scroll down. By the way, this is going to get very mad at us. Shift, enter. Yep, very mad. There's an error. And the error is explained here, but the short of it is this is something where R is a little bit different than Python. In this Python example in stats models, the independent variables, they can be categorical. They can be represented as strings and characters and factors and booleans. That's okay. The dependent variable, though, cannot. The dependent variable must be represented numerically, 0 and 1. So that's all I wanted to point out, is like that's why this produces an error, is because we used the wrong representation of the dependent variable. And I'm gonna give you a utility here in a second that lets you like fix that super fast. But in our case, our data already has ride alcohol driver as a binary 0 and 1 numerically encoded data type. So shift enter, and then voila, I have my linear logistic regression model, my logit model. One thing that I want to point out, because I know some people like to have control, smoker, the reference group is no, and the treatment is yes. So we're only seeing the coefficient as if, like with respect to people who responded yes to smoking. And then implicitly, the rest of the model is no. What if you want to change that? So that's what this next section's about. It's a little bit weird, but inside the model, you can specify some pretty complex stuff where basically you take C, which stands like categorical, this is the variable, and then comma, you have your options to change the reference group. So in this case, I'm changing the reference group of smoker to be the reference group to be yes. Therefore, the treatment becomes no. Jonathan asked about like doing OLS the old-fashioned way with matrix algebra. Absolutely. We'll do something similar to that, but you could also just do it the hard way with NumPy. But for reference group stuff for now, this is basically the block of code that can allow you to switch the reference group of any given category. So shift enter, just to prove it, mostly to prove it to myself. Now this is a bit of a word soup, but all of that results in treatment no. So now the treatment is no, the reference group is yes. And then here's a practice exercise for you to put all of it together, change the reference groups for both smoker and one of the other categorical variables, like driver's license, DL. That'd be one that you could mess around with. Now, Jonathan asked a question, can you do things with matrix algebra? That actually leads into the next section. So part one, we did nothing but ordinary least squares regression, writing out formulas. That's not really the default in Scikit-Learn. That's not the default in stats models. I want to show you how to do that with tables of data or matrices of data. So for part two, and we'll go pretty quick through this, df.columns, like, okay, these are my columns. To do the stats models, so not stats models formulas, stats models API, there's another OLS that we saw that was all caps. Let's go through that. We have to define our tables of independent and dependent variables as tables of data or vectors and matrices of data. We cannot just write out the words in a formula. The formula is gone in essence. So this is pretty common. So I'm going to create an object called dependent variable, which is just going to be the column write alcohol driver. And then I'll preview it. Shift, enter. Okay, cool. Zeros and ones. I think we're golden there. And then the numbers for the samples. All right, sweet. I also need to create a table for independent variables. And I'm going to draw that. And this is built from last week where we did our location and our subsetting. So df loc, all the rows, the female and the smoke columns, and then independent variables. I'm going to use stats models to add a constant independent vars. Putting this all together, which if it's a little bit dense, feel free to like go back over this later on, but shift enter. So now I've got my table of independent variables, including an explicitly created constant column. That's what this line of code here did, of once. This would be your beta naught or your x naught, your x0. So with all of that, let's scroll down to this block of code where I'm starting to consolidate it. I define my dependent variables as a matrix. I define my independent variables as a matrix. In stats models, nope, there's no F. It's just SM. We imported the stats models base API as SM. Logit now has a capital L. These like little things are the cues that tell you like, oh, this is a different function from the same module. I define my endogenous or dependent variable, dependent var, that's the table I created. Exogenous for the independent, has constant true, missing equals drop. This is the much more common way that models are specified in Python land. And then same thing, fit, inspect, shift, enter. And like that, we now have our logistic regression that came out of it. Now, something that's important to note, let me scroll down. Here's just another example where I switch female for grade. That way you can see kind of how this is modifying and changing. But I'm going to keep scrolling a little bit further. There's some practice. But I want to go to the error. So this error where I have independent vars, smoker. Let me click plus here, df.head, shift enter. All right. Smoker is yeses and nos. Driver's license, DL is no and yes and nans. We're going to get an error because ultimately, even though we may have written this data out as strings, regression doesn't work with words. It must have numbers. So if I run this block of code, even though my dependent variable is a binary, it's still the 0, 1, smoker and DL, now the independent variables will produce an error. Shift enter. And now, like, it's going to give a big old warning. This is expected, saying like, hey, you should check to make sure that your inputs are right. In this case, my inputs are wrong. My inputs are words. These are yeses and nos. We need to convert them. Let's do that. Scroll down. Now, you could do this the hard way. You could write for loops. You could write a bunch of replace statements. Dummy variables are real easy to make, though, in pandas. So using dummy variables the quick way, there's a function, pd, get dummies. And then we just need to give it the data frame object. We'll specify what we want our separator to be. And then this is just important to make sure that the encoding works correctly. D type int64. Shift enter. And now you'll see that I no longer have smoker as a variable. I now have the dummy variables for smoker yes and smoker no. And it has produced this giant table of one-hot encodings based on all of the columns that had categorical labels or string labels or character factors, however it was represented. And it splits all of them out. So I get ride no and ride yes. I get gender female, gender male. And my separator, where that comes into play, is the original variable name or the original column name, separator, and then the factor level, so to speak. I hope that's cool because, man, I really like. Oh, perfect! Somebody read my mind. This is a lot easier to do in Python, in my experience, than some other tools. Someone just brought up a point that I was going to make a tricky question out of. What about nans? So let me okay. Actually, we don't need to convert anything. So this sample here, that's how I created the gender column. I just took the existing female, I converted it, made it a gender column arbitrarily. So that value was also missing. So for row 3, for the gender column, the value is missing. Get dummies kind of does weird stuff. It will just encode it as 0. Now, how do you want to deal with that? Like that's important to note that it doesn't retain the missingness in this case when you do get dummies. What it's asking is like, was the value female? Yes, 1. Otherwise 0. Was it male? 1. Otherwise 0. In which case, a missing value is always the otherwise, which means it will be 0. How do we deal with that? Well, in this case, we're just going to take a shorthand. I'm going to scroll down. I'm going to do 3 steps. df new, pd get dummies. I'm going to do that whole command. And then I'm going to drop all incomplete observations. This is the brute force way that I'm doing it because this will eliminate all of those things. But it's something you have to be cautious about with your own data. How do you encode missing values? Do you drop them before or after doing these dummy operations? Do you subset and then convert? That's really up to your research process. But in this case, df pd get dummies, df new drop in a, df new head to inspect, shift enter. And now we're down. We don't have any incomplete observations, and we have much more sensible data. And this is what we'll use from here. And what's important to note is like, okay, let's do df.shape, dfnew.shape, shift enter, and we can see, okay, we lost about 1,000 observations from the data. There's other ways to inspect missing data. We don't have time for it today, unfortunately. Scrolling down a little bit further, so let's start using that. So now we can explicitly define dependent variable df new. We had ride yes. So that's where if yes, then 1, otherwise 0. Independent variable smoker yes, dl yes. So this whole process here is what allows us to start specifying. If our data only came as categoricals, we could use get dummies to very quickly get the data frame that we need to start importing our data sets. Shift, enter, voila, logistic regression. Another thing that's worth noting, if I scroll down to warning, smoker yes and smoker no, DL yes and DL no. Methodologically or like analytically, not appropriate, not right, not good. Python will do its best though. It will try so hard, and it probably won't even produce an error. Well, actually, it might produce an error in this case. But let me run this. Shift enter. And if I scroll down, it still tries. It tries its best, and it gives some coefficients, and it gives some model information. But the truth is the model did not specify because I did not choose my variables correctly. I did not define my independent and my dependent variable sets in the correct way. And there's also like lots of warnings down here that seem to indicate something went wrong with my model. And that's just where you need to understand statistically which models you can or cannot choose. Does it turn nan into 0 or delete nan? With respect to the dummies, when we created the dummy variables, the get dummies will turn them into zeros by default. But that's also why we just deleted all of those rows. So those observations are no longer valid in the data set. So none of those rows were included. Closing this out, scrolling down, we're coming up on break time. DF new columns. You can just like watch me go through these next steps. This is just a little practice exercise. Exporting models, like what do we do with this? Okay, so I'm going to create a model. And what I can do, Shift Enter, like, all right, sweet. I created a model object. Don't worry about the details. It has variables and stuff. What I can do is I can look at like, okay, model outputs results summary, and I can store that table of data in the model output. And just to check, I can print that real quick. Okay, yep, that's all there. Cool, cool, cool. Scrolling down, our tables attribute is actually a list. So the results are actually like table 1 and table 2 in the context of the model in Python. Scrolling down, so we can access that and we could say models output table 1 brackets. This would give us the coefficients. And then lastly, okay, let's make it a data frame. And just like last week, export the data frame to CSV. PD, data frame, model output tables 1, final table. Cool, we've got our coefficients table now, and some basic stuff like confidence interval, p-values. Export to computer, header, false, index, false, just because I don't need these ones and zeros that are or like 0 to 6 and 0 to 4. Last step, Shift Enter. And like that, I now have this logistic regression model CSV, which is over here on the left, logistic regression model CSV, double click. And now I have a table that I could open into Microsoft Excel, put into Microsoft Word, report in whatever way you see fit. Going to an earlier question, Jonathan asked if you could do OLS the old-fashioned way of matrix algebra. The package you want to look into is NumPy. I'm not competent enough to do it on the fly, but like the import NumPy, like NumPy is a math-heavy module. I don't remember enough of the functions to be able to coherently demonstrate it on the fly right now, but it's all about number operations, matrix algebra, linear algebra. You can also put in equations, and NumPy will help you derive or integrate them on the fly. It's a very powerful package, and it's all centered around matrix and array and tensor structures of data. So yeah, if you want to write out OLS from scratch, you're absolutely welcome to. It's been a long time since I did that. For those of you that had those questions about nans being turned into zeros, which is like that's a weird thing. You could always go to the pandas get dummies function and see like I left out a lot of information. I have to. I mean, we only have time for the tip of the iceberg for a lot of this stuff. You could, as part of getting dummies, require it to also create a factor column that is representative of a missing. So then, for example, with gender, you would have male, female, and missing, which would be converted to 3 columns, which is gender male, zeros and ones, gender female, zeros and ones, and gender NA, zeros and ones. So if like male is 0, female is 0 because the original value was missing, then the new dummy column for NA will have a 1. And then you could use that column to subset and select and filter out rows that way as well. We're now on part 4. Part 4 is just kind of like the round out of the first half of this workshop. And this is where I said a lot of these models follow the same structural patterns. So let me give an example of that. So with step 0 in this stats models example, I create my variables, I define my variable sets. I'm going to specify my model. I'm going to fit my model. Then I will inspect the model. Shift enter. And then each of these steps results in me producing a logistic regression model. By extension, going further down, let's do it again. There's a module called Scikit-Learn, or Sklearn is how the module is called in Python. Scikit-Learn has a logistic regression function. I define my variables just to get my data set up and set up correctly. There's a few little details that are a little bit different, but you can work on that on your own. I specify my model. I fit my model. I inspect my model. So 1, 2, 3 steps, shift enter. Now, Scikit-Learn is a little bit less generous with the amount of information it gives, but we can still get the coefficients for like our parameter, for our terms, our independent variables, and our intercept. We could score it. We could manually do a lot of things, but ultimately that step 3 comes out of step 2 the same way it came out of step 1 previously. Scrolling down, the pattern applies again. Scikit-Learn, define your variables, get everything set up, make sure you have your data, specify the model. In this case, the model is a neural network, a 2-layer neural network, each with 10 nodes. I have a neural network, I fit my neural network, and then I can inspect my model. Shift, enter. This might take a second to run on your computer, but now I've done quite a bit with machine learning, and these are important things to me, like what is your loss score? Like, I want to know what your loss function was, and I want to know what your loss parameter is. So I can now inspect my model, and then this is just like a weight matrix. Nobody actually reads these, to my knowledge. There's ways to diagnose them, but if you've ever heard that neural networks and machine learning is a black box, this is the black box. This is the like sequence of numbers that then results in the complex prediction. And then obviously we can just score like, hey, did it do well? Like 28% accuracy is not great. But I also don't know that this data lends itself towards classification in an easy way. If I scroll back up, though, what's important is it follows the same steps. Specify your model with whatever function you need and whatever options it requires. Fit your model, and if you need to, tell it what the data is. Step 3, inspect the model to look for the metrics and performance and parameter estimates that you care about. Okay, so with that, let's scroll down and let's get to really the second half of today, which should go a little bit faster. It's also totally different. Plotting and graphics. We're not going to do too many super complex things. I just want to get you started with getting basic visualizations of data on screen. We're mostly going to use scatter plots, but we'll play around with a few other options as well. Scrolling down, we're going to use the new data set, by the way. So this is where it's important, like that you had California School, caschool.csv, downloaded today. And what this California Schools gives us, key metrics of interest: reading score, math score. So what is the average math score of a school somewhere in California? What is the average reading score? And then other metrics, demographic information, economic information, location data, like nominal, like what county are we even talking about? So this is all about California schools and test scores. So let's do that. Let's create a California school object using PD, read CSV, read the CSV file, and then we'll do CASchool head to inspect it. Shift enter. And then like, okay, we've got a lot. We've got different types of information. Okay. Scrolling down, let's start to visualize this. This is a lot of information. There's more than I want to like read through. I'm going to import some modules. One that we need to be aware of is matplotlib. This is If there is a core plotting library in Python, it's matplotlib. Like many tools, many of the most advanced visualization packages are built on top of this one. So this has a lot of base functions, but it's also not very pretty, so we're not going to use it too much. We will use a couple utilities from it, though, so we will import it as PLT. So that's our matplotlib. And then Seaborn is literally built on top of matplotlib. The Seaborn module, SNS, gives us a lot of like really handy and easy to use ways to visualize data. Shift, enter. Scroll down a little bit further, and let's get started. And just watch my screen for now, Seaborn. Their website is better than me, to be blunt. So like if you want to really learn in depth how to do some of these visualizations, I do strongly encourage you go to their website, check out the tutorial. And in the tutorial section, you'll find like, okay, what type of plots do you want? Do you want relationship plots? Do you want categorical plots? Do you want regression plots? Are you having trouble with colors? They have a very clean and neat and well laid out website. That's why I'm walking you through some of this stuff today. Okay. So just be aware their website is beautiful, really well laid out, very helpful, in my opinion. So going back to the code, SNS Seaborn relplot. Relplot is going to be a very high level function it stands for relationship plot. In this case, it's going to be a scatter plot. So let's get started. Relplot X, pretty intuitive. X-axis reading score, Y-axis math score. The data is California schools. If you're familiar with R or some of these other packages, this is a pretty intuitive way to specify a plot. But California schools, and then I specify in other options inside my function where the different variables I want belong. So all of this will create a scatter plot object, and then that was using Seaborn, SNS, PLT show to literally show the plot to us on screen. And then PLT close, this has to do with the background info. What Python's doing is it creates a figure object in memory, and it starts to tweak that and edit that. But sometimes it will produce duplicates if we're not careful. So PLT close just like sets it and resets it to the beginning so that our next plot starts with a clean canvas, so to speak. So let's do this. Shift, enter. Ta-da, scatter plot. Now, this scatter plot needs some work. Data visualization is all about communicating information visually. You can use it for analysis and like diagnosing things, in which case you want to have very precise controls. But I want to focus on using some aesthetic markup to make it visually more appealing, because maybe you're communicating with an external audience and you're trying to use data in that way. Scrolling down, now this example here just puts it all together without all of the annotations. So scatter plot is this, then PLT show, PLT close. Shift, enter, same output. Now, just like every other function that we've been talking about last week and this week, there are more things that you can add. And with plotting and visualization, there's a lot. So let me scroll down. You can always read the documentation. You should always read the documentation. But here's the giant list of options. And Quargs literally means there's unlimited other options in certain contexts. But the key things that we need to know about are here, the ones that are explicitly defined. We're not going to use all of them, I promise. But let's use a few just to start seeing what they do. Scrolling down, scatterplot, SNS, railplot. I've done everything the same as before, but I've added one line. Q. So maybe I have a theory or an assumption, or I just know something. Maybe I know that the average income of like average family income in a school district has something to do with test scores in that school district. Maybe there's a correlation there, maybe there isn't. But I'm going to use hue to effectively color code. So shift, enter. And now I see, like, I've started to add some layers of information. I didn't even have to pick a color. Seaborn will default to a certain color set unless we override it, which we'll get to. But now we can see there's a concentration of, like, okay, for high math scores and high reading scores, the average income seems to be on the darker side of this continuum. Now, this isn't making any causal explanations, but we're starting to see that. And then the lower income groups or lower income districts also represent lower test scores. Let me exit my annotations and let's start building this up. Let's build this up into a more robust visualization. Scrolling down, what about size of school? Does enrollment total matter? So there's a size parameter. So all of these dots are the exact same size. But now if I override that with size equals a variable, so these are all columns from the data set, and I'm going to have the size of the dots be proportional to the enrollment total. Shift Enter. Now I start to see, like, my marker is going to be bigger than some of these dots. So, like, I see some big dots there. I see some tiny dots in other places. It's a little bit hard to distinguish, though, and maybe there is no pattern. Maybe that's why it's hard to distinguish. But we can now make this a little bit, we can change this. Because right now it's a very, at least on my screen, a fixed square that's relatively small. I can make it bigger. Let me scroll down. And let me do a whole bunch of things all at once, just to show you how rapidly this expands. Seaborn relationship plot, variables X and Y as read score and math score still drawn from our California schools, color coded by income, sized by enrollment total. I can even control what those sizes are. So 50, I think 50 pixels is what that means, is my small end, 250 is my large end, and then it will normalize within. So it rescales the values of enrollment total to meet these. Style. We'll see what style does, but I'm going to assign style to a categorical variable that was, some of these school districts have K through 6. Other school districts have K through 8 grades. So depending on how those schools are structured, maybe we see some different outcomes. And then height. Height is literally the height of the plot. Because if I scroll up, this plot's a little bit small. And it might be a little bit small on your screen. Maybe I want it bigger. And then aspect is aspect ratio. Now, the details of each of these might be a little bit weird and hard to grapple with at first. The point is, we started with a small subset of, like, just the data and just the variables we want, and then we added on layer after layer after layer of options to build upwards. Shift, Enter. And now if I scroll down, I have a much bigger plot. It's a little bit easier to read. I can actually distinguish the size groups. And then there was also a new option for style. It's a little bit hard to read because the colors are still kind of bad. But now we see dots and X's representing the different categories. So here's, like, some dots and X's right next to each other. So just like doing that little procedure of writing a Python function and putting a few parameters inside of it, we created a scatter plot. And then we morphed it, we added some color, sizing, scaling, and reshaped the whole plot. Now, so colors. By the way, I said there was a tutorial on Seaborn's website for colors. Check it out. I am not a data visualization expert at all. I will never claim to be. I know how to get these functions up and running and how to use them. I am just not great at, like, picking colors and doing aesthetic things overall. I try to do a good job when I have to. But, like, to do that, I go and look for, like, pretty colors that other people have made. So from the link that I've highlighted on my screen, there's a whole, like, giant tutorial that does a really good job of explaining categorical color sets, sequential color sets. One that I learned from there is simply called cool warm. This doesn't exist in our data or anywhere. This exists in the Seaborn module. So it knows my color palette is going to be cool warm. Shift, Enter. And now this is a little bit easier to read. So now we have, like, dark red to dark blue, so a spectrum, rather than starting at like white and then moving up in some direction on the color wheel. So you can mess around with the colors. If I scroll down further, now we can go a step further. All of this was to say, let's create the plot. All right. Once you've created the plot or a figure, you'll hear a variety of different terms to describe it. But once we have this figure, this object here has methods. We can then update it and overwrite it. So, for instance, if I scroll up, there is no title. So, like, no journal editor is going to accept you if you try to submit that. My X and Y axis labels are automatically generated from the name of the column I gave it. But what if I want to call it something else or give a more meaningful definition? Let me stop annotating. Let me scroll down. That's where we could do scatter plot. There's a method I happen to know exists. Read the docs. You'll discover all of these things. Set axis labels, X var, Y var. So average reading score, average math score. Scrolling down a little bit further, scatter plot has, for the entire figure, you have to do figure level editing. And so there's a lot of weird moving parts, and hopefully I'm giving you a framework that you can edit and play around with as a playground. But scatterplot.fig.subtitle, super title, this will give us the title of our plot. So all of this together is just me making a scatter plot. Shift, enter. And if I scroll down, because not all of it fits on screen at this point, now I have a scatter plot with a title, with axes I've labeled intentionally, with all of the other markup and styling and choices that I have made. Scrolling down one little bit. Last thing that I want to point out, last thing that you can always do, because let me scroll up real quick. This here, this plot, it only exists here. Okay, it's being rendered as an HTML image. There's a lot of fancy pants stuff happening in the background. But when I close this picture goes away. Now, I could upload this file to GitHub. Lots of people do that. They'll upload Python notebooks to GitHub that have their outputs interlaced with code. But odds are you won't do that for a lot of your reporting. You'll have to report Microsoft Word documents and write-ups and reports. So let's export this. Just like we could export our data frames as CSVs, our big block of code, this creates the plot, this edits our axes, this edits our title, this step here, scatter plot, save fig. And I can save it to a file of my choice, scatterplot, math, read.png. And if I do shift, enter, so I'm still like saying, hey, show it to me, then close. So I'm still getting this output here. But if I refresh, I can now see that in addition to all of the data on the left, I now have a file saved on my computer. So now I have that image saved. Now this, like you could imagine where you might make this a lot bigger. You could write, let's say you get a lot better with Python, you could write an iteration, a for loop. So a loop where you go through column after column after column, or data after data after data. And for each one of them, it does a process where it goes, looks at the column, creates a scatter plot, saves it as a name, goes to the next one, creates another scatter plot, saves it as a name. And you could rapidly generate visualizations for every component of your data and export it and save it to your computer. I know a lot of people like want to know about that, so I just wanted to bring it up. It's easy peasy. You have your scatter plot, dot save fig, and then give it a file name. Simple as that. There, as always, there's more options, but that's the basics. Scrolling down a little bit further. Practice time. Practice. This is probably going to be the toughest practice that I have created. So we have California school head, shift enter. This is just meant to give you like, okay, what is the snapshot of my data? And then like plug and play, mess around. I encourage you to really like You won't learn Python from webinars like these, just in terms of watching passively. That's why I've tried to create these hands-on components. I really would encourage you push yourself to try and do these later on. Scrolling down, scrolling down, scrolling down. Oh, this, I want to point out, this is a single plot. But we have some other options to get multiple plots all at once. Sometimes layered on each other, which may be because you're doing like if you're doing some type of regression model and you think there might be different levels of effects or different slopes, whatever, for different categories within your data, different subsets, there's ways that we can segment and break that down. And to do that, we're going to switch gears. This was all in the service of scatter plots. But I want to shift gears and show you like regression plots and categorical plots. So part 6, column wrapping with plots. Column wrapping is kind of a weird phrase to hear the first time, but it makes sense in the context of Seaborn plot functions. So that's why I said it here. That way it's a little bit more intuitive as we build up. So we can inspect our data, California school head, in part 6. We could then create a category plot object. So I'm just going to create a cat plot with X is counties, Y is my test scores, California school, height, aspect ratio, kind, box. So this is going to be a box plot. Now I'm zooming over the details of categorical plots overall. We spent more time on relationship plots just to see how things built up. But for this, just trust me, this, I hope, works. I'm going to rotate the axes labels or the X labels so that they're readable. Shift, enter, and I just want you to see what we're dealing with. So now, a colleague of mine, this is her favorite type of plot, box plots. She loves box plots. She thinks they're the best thing ever in data visualization land. So here's a giant set of box plots where everyone is representing a single individual county. Okay. Now, this is not like column wrapping. This isn't what I promised of like, let's split it out by subsets. Although I guess counties are kind of a subset. And this gives us a notion that it automatically colors them. The colors have no meaning. The colors literally just follow a cycle from beginning to end, and it circles through a color wheel. So let's start subsetting this information. For instance, these are average test scores, like aggregate average test scores, not math or reading, but both combined, with respect to individual counties. But if we remember, some schools are K through 6, other schools are K through 8. So what if we want to inspect those differences? Let me scroll down. So I'm going to create another category plot, X, Y, data, da 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 da. All of this is the same as what we had up here. Okay? The only thing I've added now is hue. So comma, hue, grade span. So if we remember to the scatter plot, hue had the effect of creating a color spectrum, in part because the variable of interest was a continuous variable, or at least a numeric representation. In this case, the variable grade span, which if I scroll way up, grade span is categorical, K8. It's only showing K8s on screen. There are also K through 6. If I scroll down, color code by hue in this context behaves a little bit differently. Shift, enter. And now, we can see like not all counties have discrepancies in their types of schools, but we can see for some of them, like San Diego County, we see side by side a box plot of their average test scores and different distributions, different averages, different quartile ranges, different like outlier, the outlying step, the tails that go beyond a box plot. So hue allows us to subset things right away, like and get side by side comparisons. Versus column wrapping. Let me scroll down. So in the next example, Same deal as before. I comment out hue. That way, like, so this is something you could do. You could comment and like swap out which ones show where. I'm going to instead define the column parameter as grade span and column wrap 1. We'll fiddle with that so that you understand what the number means. But let's just see what this does. Shift, enter. And now, if I scroll down, it produced it instead of putting the box plots side by side, it literally subset the data. So now K through 8 is its own plot, and K through 6 is its own plot. Depending on what your analysis is, depending on what you're trying to do, different approaches matter in different ways. So if you wanted to get a whole bunch of scatter plots by like a nominal variable that had like 30 different categories, that would be a way to just get a whole bunch of scatter plots and then a whole bunch in a row. Now, column wrap 1 literally means I want one column so that you basically have one plot per line or per return. Let me close this. Let me scroll down. Let's change that. So let's do same thing as before. Column wrap, grade span, column wrap 2. Shift, enter. Oh, I just hit enter on accident. Shift, enter. There we go. And now this is unreadable on my screen at the moment. I could try to make it a little bigger. There we go. I mean, this is probably a bad example from an analytic point of view, but instructionally it tells us like, okay, so now we have 1, 2 columns. Now in this case, we only had 2 categories, so we only see the 1 row. If we had 3 categories, then we would have 1 plot, another plot, and then line break the next plot. All right. Let me exit out of that. Let me scroll down a little bit further. Because, practice. Always practice, people. Scroll down. Regression plots. So this is where the distinction might be a little bit more valuable. In the example up here, these giant sets of box plots, it would be difficult to justify this because it's an overwhelming amount of information. It's a lot of different categories for county, and then we separate it out further. The color coding scheme is kind of dodgy. But the idea is we could use hue to, let me scroll up, to get these side-by-side comparisons for each of the original x-axis nominal categories. Or we can use column and column wrap to get these subsets literally split apart into separate plots. Let's do that with a regression line. Simple regression, don't worry, we're not doing anything crazy for this one. If I scroll down to regression plots, regression plot object, Seaborn, LM plot, linear model plot. Average income is our x-axis, we'll call that our predictor, and our test scores will be our response variable, our dependent variable. Just a real simple regression model. So this is our data with school. Height and aspect, we'll keep those the same. Fit reg, so fit the regression model. Confidence interval 95. Shift, enter. And then you've all seen, I hope you've all seen this plot before, where you have your scatter plot, you have your line of best fit, you have the confidence interval around the line. Easy peasy, straightforward. But let's start subsetting that data. This is where hue and column comes into play, that column wrapping. Scrolling down, hue, grade span. Again, same categorical breakdown that we were using before. So shift, enter. And just like that, all I had to do was specify one component, and now I see 2 different regression lines, which might help me diagnose like, do I need a mixed effects model? Do I need to do some hierarchical modeling? Do I need to really interrogate my data set and just split it apart? Are there just totally different populations contained in the same sample? Yeah, that's up to you. That's up to your own like diagnostics. But at its core, it didn't take much work for Seaborn to simply use the color coding option to then subset according to the variable of interest. Scroll down, and I'll do the same procedure that I did before. So I comment out hue, so that's no longer active, and I instead replace it with column great span and column wrap 2. Maybe this would be more appropriate in some cases. Shift, enter. And now I see side by side like an LM plot for one, an LM plot for another. I also get a better sense of like how many samples are represented. Something that is nice to know, something that I had to check the first time I ever did this. These scales are the same. So this x-axis, like the intercept points, the scaling, the limits of our plot in either direction, the scaling is the same. So it is easy to visually interpret the relative size, distribution, and placement of data in that like loose visual analysis way. Practice exercise. The last thing that I want to talk about, modules with built-in plotting. So I showed you like all of this is Seaborn. Seaborn built on top of matplotlib, but this is visualization on its own. This is like when you have the data either as an array or as a vector or a spreadsheet, doesn't matter. You have the data and you're ready to visualize it. And maybe it's in a pipeline. Beginning with last week, you open the data, you start to inspect it, you subset it, you slice it, you dice it. Then you build a regression model, then you produce fitted values. Those fitted values are then in a vector or an array. You can then put that array inside of a plotting library or a plotting object, like what we've done with Seaborn. So you can build it into this whole big process. One thing I do want to note is a lot of other modules, pandas and stats models in particular, with particular relevance to the sessions we've been doing today, some of them will have pre-built plotting functionality. Let me scroll down and give an example. So in part 7, and I think this is the last part, and then I could spend a few minutes talking about some other stuff, but let's finish this out. Part 7. Let's say we use pandas. Pandas has a guide on visualization. California schools, average income, plot, histogram, da 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 da. This is a pandas object. This is our pandas data frame. It has a method plot, just like describe, just like mean, just like any of the other things, or like drop in a drop missing. That was a method. So we could do plot, histogram, bins 30, shift, enter. And like that, I get a very simple, it actually uses matplotlib. It's built on top of that. And it gives us a plot right away. So for simple plots and like simple visualizations, some of the modules you already use will probably have pre-built functionality. That's like the long tail of visualization and plotting. One thing that you will struggle with is they don't often allow you to, what we did with the scatter plot, like change the size, the color scaling, the palettes. If you like overwriting and updating that information is very difficult and very challenging when you're using pandas. It can be done, but it's hard. But in terms of like you inspecting your data, sometimes it's the faster way. So I just wanted you to be aware that a lot of these tools are intermingled and intermarried with each other. Pandas has visualization options. Another example, California school, reading score, math score, plot, density, shift, enter, and right away I can get just a density distribution, a kernel density estimate, and segmented by my 2 different variables. And I can see like, oh, reading scores seem to be a little bit higher than math scores, but if we were to run a t-test, I bet they'd be about the same, or super duper close. But the point is, pandas has some pre-built functionality. Stats models does as well. I found it very challenging to use when I first tried to figure it out. But let's walk through that example. So stats model, shift enter, df head, right, da 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 da, all of our variables. Let's just make sure we know what we're doing when we build a formula model for ordinary least squares for age and a bunch of predictors. Shift enter. Okay, cool. I have a regression model done. So like this is all from the first half of today. So we created this linear regression. If I scroll down, I can do something a little little bit dense, but I can, in essence, create a stats models, graphics, plot, partial regression grid, results, fig equals fig, all of this together, if I do shift enter, will give me partial regression plots of particular variables regressed against others. Or well, regressed against the dependent variable age. This could be helpful for diagnosing like skew or imbalances or non-linearities, what have you. So like the packages themselves, like stats models, has some pre-built functionality that you may find useful. In order to make use of those, you have to go through all of their documentation. But a lot of the things that I talked about, although it doesn't immediately seem obvious, a lot of the options and parameters that go inside of those functions, they will end up relying on matplotlib or Seaborn. So if you have an understanding of Seaborn, it's very easy to like mentally wrap your mind around how these other tools are working. And I think in my last couple examples, I could do an influence plot in stats models, but that's the high level like outcome of part 7 is just addressing the fact that different tools we've used, like pandas, like stats models, will have some pre-built functionality that might allow you to do some quick plotting that will help you like just inspect your data. Oh, I think my code stopped running. Let me go look at it. Let me scroll down. Oh yeah, and then we have this hot mess. We like this is almost impossible to read. I'd have to do a lot of work to figure out what are my options to make this bigger and more readable. Same thing applies down here for the like regression on the exogenous. Da 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 da. I see a question has popped up in chat, but that's the end of our code. I have a few other things that I want to mention, but with respect to the code, before I switch back to the PowerPoint, questions, comments. What do you think? We're actually a few minutes early today, unlike last week. Let me know. Let me look at the chat. Can we have two types of plots on one graph, e.g., a histogram and density plot superimposed? Yes, you can. Here we go. Here's an example of like a count plot that seems to include both like histogram bins as well as a distribution. So the short answer is yes, you absolutely can superimpose. If you're familiar with ggplot in R, Seaborn and matplotlib work the same way. So we did the super high level like relationship plot or cat plot, but you can go real deep down and say, I want a KDE plot, create it. And then I want a histogram plot, create it, layer them on top of each other. And then I want a rug plot on top of that. And then I want X and Y and Z. Like you can keep layering those onto each other. It is a little bit weird. It's a little bit more challenging from a technical point of view, but it's absolutely doable. Great question. I provide links just so that you can remember, like, oh yeah, these are the packages you use, stats model, scikit-learn. For those of you that really want to get into machine learning or just statistical analysis using advanced modules, which, I mean, statistics and machine learning, arguably, there's a lot of overlap there. One thing I can't recommend highly enough is a website called Machine Learning Mastery. The guy who created this website, I mean, he has like a book and he has a few paid products, but the website also just has tons, and I mean tons of blog post style tutorials where he explains like how do you do time series analysis in Python? How do you do bag of words text models in Python? Here's a module, here's some code, and it interlaces very well. It's a very useful website. There's a couple links to general resources that you might find useful. Talk to your librarian as well, or someone who's equivalent to your librarian.